What I will be talking about is magnetically induced holographic composite inflation. And it's a work in collaboration with Dr. Moslem Ahmadband, who was a researcher at the School of Physics of IPM, and Professor Bitafsir Fadafan at Shahrid University. And it's based on this paper, which was published in PRD. We now know that primordial inflation, which is a period of accelerated expansion, can solve the problems of the standard Big Bang cosmology, problems such as flatness and also the horizon problem of the standard cosmology. It also provides a mechanism for generation of the fluctuations, the density perturbations that lead to the structures we observe today. The most vanilla slow-roll single field model is compatible with the latest results of the Planck 2018 observation. We know that the power spectrum is red, and it's almost scale invariant though. So this NS, which is called the scalar spectral index, is very close to 1, although a bit smaller than 1, and that is interpreted in the form that inflation had to have an end. So basically NS had to be smaller than 1. And we also know that the spectrum is almost Gaussian. There are different shapes for non-Gaussianity, local, equilateral, just orthogonal. But most of them, I mean, the variables, the FNL variables that are assigned to these different shapes, they are they have turned out to be small. And the spectrum is adiabatic. So basically, just one component inflationary model is enough to describe the data. And there is still no sign of gravitational waves. So Planck, along with BICEP2 and Keck array, has put an upper bound on the tensor scalar ratio at the scales of 2,000ths of megaparsec to be, I mean, this ratio is smaller than this number, 56,000ths. Energy scale of inflation, single field inflation, could be related to this tensor to scalar ratio by this relation. So do you see my cursor? No? Or yes? Hello? Can you see my?
Yes, yes.
You see my cursor, okay. So the scale of inflation is related to tensor scalar ratio through the first equation in this slide. And you see that 100, the value of 100 plays a crucial role. And basically, if R is close to 100, the scale of inflation is very close to the Gauss scale. And since the upper bound on tensor scalar ratio is still above 100, so there is still room for working with Gauss scale inflationary models to be responsible for the generation of the just the data, the density perturbation data. There is another relation for the single field inflation that relates the excursion of the field in the field space to the tensor scalar ratio by this relation. And again, 100, that is a critical number that appears in this relation. And so basically, if R is bigger than 100, excursion of the field is bigger than M Planck. And this is usually problematic for fundamental physics, for embedding the inflationary models in fundamental physics, especially string theory. This is because, for example, in supergravity, in order to be able to ensure the flatness of the potential on scales beyond the limit of the validity of the theory. So in order to be able to embed such models, you have to assume that delta phi over m Planck. So such terms appear in the superpotential and also in the Kähler potential, and so you have to be able to ignore them, and so you have to do fine tuning for those operators that would naturally appear. And in stringy models of inflation, what one finds out usually is that the geometrical size of the region in which inflation can happen is usually at most of order of m Planck, as pointed out by Bauman and McAllister. So this is what I consider a realization of the distance conjecture in the swampland conjecture, where when one approaches the Planckian displacements in the field space, they conjecture, Auguri and Vafa conjecture that a tower of massless modes will appear, and so the single field description of the theory breaks down. Because of these reasons that I mentioned, and because it's still the upper bound on tensor scalar ratio is bigger than 100, still large field models are of interest. The other problem that usually occurs when one tries to embed inflation, not necessarily large field inflation, in the string theory is the eta problem. So you construct an inflationary sector that works fine, but you want to do moduli stabilization of the other moduli, the moduli other than the inflaton. And then you will get corrections proportional to R phi squared, where R is the Ricci scalar. And in an expanding background where R is about h squared, 12h squared, so this will lead to eta problem. So this could be understood that in the presence of vacuum energy, soft masses, including the inflatons, receives correction which are proportional to the V, the vacuum energy over m Planck squared, and thus they receive corrections of order h squared. And for example, in KKLMMP model, volume stabilization of the stabilization of the volume modulus leads to this correction that produces the eta problem. So you have to do fine tuning to get rid of this, this problem. So in this talk, I try to elaborate the magnetically induced holographic composites inflationary model that tries to avoid these problems, hopefully. So the outline of my talk is as follows. I will go through the setup of holographic composite inflation with magnetic field. Then I talk about the comparison with observation, how it violates the light bound. And then I will talk how this model could be treated as effective single field model, and then I will conclude my talk. So the setup of the theory is a lot inspired by this ADS-QCD correspondence. And so in this setup, you have D3, D7 setup in the type 2 string theory, which is dual to n equals to 4 large 𝑁𝑐 super Young mills with 𝑁𝑐 gauge theory. And D7 brane is a probe in the background, which is induced by the 𝑁𝑐 D3-branes. So we want to know how one should just deform the background such that inflation is realized. So strings that are stretched between the D3-branes, the stack of D3-branes generates the UN gauge theory, and the 3-7 strings are quark fields in the fundamental representation of the SUNC. So, so you have a strongly coupled gauge field theory, and so there is a gravity side which is weakly coupled, and it's easier to be studied. So this stack of the three branes induce such a metric solution, ADS5 cross S5 solution, which is given by this equation in red. So GUV is the asymptotic value of the gauge coupling. R is rho squared plus L squared. L is the distance that, I mean, the coordinate that separates, one of the coordinates that separates the stack of three branes from the seventh brane. And rho is the coordinate that, the radial coordinate in the four-dimensional space which are not parallel to the three brane. And it corresponds to the scale of the gauge theory. This R, big R that has appeared is the ADS length scale given by the value of the gauge coupling, number of D3-branes, and alpha prime, where alpha prime is the string tension. And we also assume that in the three-dimensional metric on the D3 brane is given by the Friedman-Wack FRW metric. So quark field condensations are fields that break the chiral symmetry of the theory, and so we want to just know how this theory, I mean, this condensate evolves, and if this evolution could be realizing inflation, and how this embedding function L rho t should look like in order to realize inflation. So one writes down the action for the D7 brane, and it takes this form, this red equation, where the introduced variables gamma is defined here. T7 is the tension of the D7 brane, and L prime is the derivative with respect to rho, and L is derivative with respect to time. And so we want to know the gauge running of the gauge coupling parameterized as e to power of phi, where e to power of phi is given in terms of the UV gauge coupling times the function beta r, which, as we will see in the case of the magnetically induced chiral symmetry breaking, take this form by lowest equation in red. And this is the result of when you turn on the magnetic field, you see that there is this relation between beta and the value of the magnetic field and rho and L. Um, so you can derive the equation of the motion for the embedding function given by the upper most equation. And then you can derive the energy momentum tensor from this equation, familiar equation, and the T00, which provides the energy density, dimensionless energy density, will be given by this expression, where epsilon naught is the energy density from the static embedding function when there is no expansion in the three-dimension three branes, on the three branes. And so it would be computed from L, which is obtained from this equation. So having the energy density, you can find the Hubble parameter that by which the expansion on the D3 branes would occur. And we are interested in inflationary background. So to first approximation, we assume that H0 is constant. So we try to solve this. So we start with this ansatz, but we want to be consistent. So L and epsilon should simultaneously satisfy equations, and so you should basically converge to a fixed point. And the way we have the way that we have guaranteed that is just by recursive iterative um, just approach. So by the way, I should mention that Evans and his group had tried in 2010 to realize inflation, and just at this point they had to stop and saying that the energy density, I mean the form of the energy density that would be obtained is just too steep and to be realizing inflation. So we were dubious of that, and we tried to show that basically their model, I mean, the model that they had put up together can indeed realize inflation. So we started with their initial ansatz for H naught and B, and we used solved this equation for L using the ansatz for a scale factor to just be pure de Sitter. And then we solved it by these boundary conditions. So once we had L, we are able to obtain epsilon through this equation again. And then we plug this from this epsilon, one would be able to obtain the Hubble parameter, then find the scale factor again. Again, feed it back to this equation, solve for L again, and you can continuously solve for this. Continuously just follow this procedure. And we stopped at the point that we thought that we have reached just a fixed point, and our criteria for that was that the second order, the difference of the second order correction with respect to the first order, so the difference between the second order and the first order solutions with respect to the first order is much less than 1. Sorry, it should be much less. And then the form of the embedding function would look like this in terms of rho and t. So from having just the embedding function, Babington, Erdmenger, and the group had shown that there is a relation between the embedding function and the mass of the quark fields and the condensate that just provide this chiral symmetry breaking in the UV limit. So M is related to the mass of the quark by this relation, and Q bar Q is just the condensate proportional to the condensate field. And we have worked with the dimensionless L, rho, M, and C. So in order to make them dimensionful, L, rho, and M should be rescaled by R, and C should be rescaled by R cubed. And if you just from the energy density that we have derived, and from the embedding function that we have derived, you just try to solve CT from this relation, obtain the condensate evolution. You will see that during inflation, it varies very slowly until it reaches its minimum and it starts oscillating. So this is basically the behavior that one would see in usually single field inflationary models that inflation end up around a minimum. So to contrast with observation, we took into account that we have been working with dimensional full parameters, epsilon, and it's related to the physical dimension full parameter by this way. And so we want to work in Planckian units. So we rescaled it by Planckian energy density. And so we have assumed that there is Planck mass is related to the radius scale by a factor of NP. This is something that one can vary, and that would correspond to just the number of D3 branes that, and gauge coupling in the UV. So this is a parameter that you can play with. And you can obtain the Hubble parameter this way, and you would see that the Hubble parameter is constant and then drops and it just decays. And so this so this inside figure is just the behavior at the end of the at large values of t, where Hubble parameter decays and you see oscillations on top of this decay. That is just the indication of this oscillatory behavior of the inflaton. And for just obtaining these behavior, we have used these values for a number of D3 branes, the tooth coupling, and NP. So we have worked in the units where m Planck is 1. So basically R, the radius of just the ADS is just equal to NP. So as you see, a large number of D3 branes, I mean a stack of large number of D3 branes is needed in order to realize this scenario. So we try to see if the model can comply with observations. So in order to make sure of that, you have to make sure that the epsilon parameter defined in this way is much less than 1 during inflation. The other parameter, the slow roll parameter, which is just given by this expression, epsilon minus epsilon dot over epsilon h. So this is also has to be small in order to make sure that inflation can be sustained for large amount of time. And number of e-folds is just given by this expression. And the t that we have been working with is just was dimensionless. In order to make it dimensionful, you have to multiply it by np. So if we are working with if we have a Gaussian scale inflation, so the number of e-folds that is needed to solve the problems of the standard Big Bang cosmology is about 60. And in the dimensionless units, for the set of parameters that I showed you before, the TCMB and T of end of inflation is just given by these values. So you have to, during inflation, two types of scalar and tensor fluctuations are produced, and you have to make sure that at the CMB scales, so the scales that exist during the TCMB, the amplitude of density perturbations is in agreement with the Planck reported value, and also the scalar spectral index is within the 2 sigma limit of, within the 2 sigma region of the Planck results. Also, we have to make sure that the tensor scalar ratio satisfies the inequality from Planck data. I'm hearing that the upper bound from Planck has been improved by, considering other experiments, and it has been reduced to something about 300s to 400s. But it doesn't change my argument in this talk. So one set of one set of parameters that can just lead to the observable values, the observed values of the parameters was the one that I showed you before. For those ones where 𝑁𝑐 is equal to 10 to the power of 7 and tooth coupling is given by this number, the UV gauge coupling turns out to be about 0.37, and NP, the length of the radius scale with respect to Planck length is about 8 times 10 to the power of 5. And you see that the amplitude of density perturbation is 2 times 10 to the power of minus 9, which is just in agreement with the Planck reported result. NS is also, and R is about 100. So we tried different, the predictions of the model for different values of NP, the ADS length. And you can see that for, tuning lambda accordingly, the tubes coupling, one can, for different values of NP, you can match with observation. So the model predicts R bigger than 100, and so naturally, as light bound implies, so you would expect that the field excursion would be Planckian or super Planckian. But one should note that the condensate that we are dealing with is a mass cube composite operator. And in order to make it to a just single field mass dimension 1 operator, you have to just divide it by some mass dimension pool parameter, which is just the cutoff of the theory squared. So basically, you can see that the field excursion, the mass dimension 1 field excursion would be this and not this one. And the cutoff, where lambda, a big lambda is the cutoff of the theory. On the other hand, you would expect that lambda, the cutoff of the theory, is bigger than the condensate of the, is bigger than the quark condensate at the minimum of the potential, where epsilon, the energy density had an oscillatory behavior. And using that, you would see that delta phi, the excursion in the mass dimension 1 operator is indeed about 10 to the power of minus 3 m Planck in the example that we worked out. So even though we obtain a tensor scalar ratio of order 100, the mass dimension 1 field, which is constructed out of the mass dimension cube composite field, remains sub-Planckian. As I mentioned in the just introduction, the perturbations from the Planck is almost compatible with an adiabatic result. And in this holographic setup, because we have extra dimensions and also we have fluctuations along the D7 brane, we may be worrying that those fluctuations would get dominant over the condensate fluctuations. And in order to just see that, if you just write down the variations of the embedding function, which would correspond to one of the dimensions just in perpendicular to the D7 brane. And look at the variations of this embedding function in terms of the composite field and delta rho. So because it has and the time, the functionality of time, basically you can write down it, this functionality as the functionality of the condensate too. And rho was the variable which was the radial coordinates just along the D7 brane. And so if you look at the 2-point fluctuations, assuming that delta C and delta rho are uncorrelated. So the 2-point function of the embedding function, which was the direction perpendicular to the D7 brane, is a combination of the the 2-point function of the condensate and also the 2-point function of delta rho. And as you see, AC squared So we have plot AC squared and A rho squared here, the coefficients of the two-point function of the just the condensate and the longitudinal mode along the D7 brane. And you would see that along in the I mean, in just around the time of the CMB scale, just horizon crossing, which was about 80. I mean, the contribution, the two-point function of delta L is suppressed with respect to the two-point function of delta C by a factor of AC squared, about 1/100th. So basically, I mean, the fluctuations of the other field is just subdominant with respect to the fluctuation, two-point function fluctuations of the condensate by a factor of 1/100th. But in order to be able to assume that delta rho fluctuations is subdominant with delta C fluctuations, you have to assume that this delta rho has had a mass much bigger than Hubble parameter during inflation. So the smallness of A rho does not guarantee that this rho fluctuations along the D7 brane remains subdominant with respect to the condensate fluctuations. So we basically have to just, I mean, in a full-fledged theory, come up with some mechanism to just suppress these two-point fluctuations. And for that, usually you have to just endow these fields with a mass greater than or equal than the Hubble parameter. So if I want to, I mean, conclude my talk, I discussed that inflation is more or less accepted as the standard paradigm for solving the problems of the standard Big Bang cosmology and generating the seed for larger scale perturbations, and connecting inflation with string theory and more fundamental physics is a very interesting avenue through which we can understand string theory better and correspondingly constrain it just experimentally through cosmology. And in this work, we focus on the holographic D3, D7 brane system in the background of the magnetic field. So something that I mentioned about the eta problem, the reason that the eta problem is, um, is solved in this setup is that inflaton field emerges as a bounded state, breaking the chiral symmetry at some energy scale. And above this energy scale, there is no bounded state, and therefore the radiative correction to the inflaton mass, which would lead to the eta problem, can be circumvented. We found the embedding function, which is desired in order to provide a long enough inflationary period through a numerically iterative approach, recursive approach. And we showed that contrary to the just previous claim by Evans and his group, the model can be worked out to just to produce long enough inflation. And not only that, it can also just provides I mean, it can provide observables that are matching with the CMB experiments. And we showed that even though the model is producing large enough tensor to scalar ratio or B mode at the CMB scales, the displacements of the canonical mass dimension 1 field, which is constructed out of this condensate field, quark condensate field, remains below the Planck mass. And this would conclude my talk. So thank you very much for your kind attention. If there is any
Um,
question, I'm happy to just hear.
Thank you very much. Thank you. Very nice talk. Any questions?
Yeah. Hi, Amjad. Good evening. Thank you.
Hello.
Yeah, thank you so much for your nice talk. I have many questions, but I want to summarize all of them.
By the way, okay. I don't know who is just
Yeah,
talking.
I'm Haider. I'm
Okay, okay. Yeah, thank you.
yeah, I'm based in South Africa now, and I have many questions, but I want to summarize some of them in one question. And it goes back to the vector fields. As you know, the electromagnetism is a vector field, and so how you can, because vector fields, even before the horizon crossing, they usually were damping, and so how you can detect such effects by only using the two-point functions analysis, because we know if you have such interactions, maybe you have to consider the non-Gaussianities like three-point functions, bispectrums, and also higher orders corrections, trispectrums, and how you can imagine and also how you can compare your results with observations, Planck data, just by considering these results. Thank you so much.
You mean the two-point function?
Yeah,
The fact,
because two-point functions are related to the free parts of the model, but usually if
yeah,
if you want to see the inflationary effects, usually we have to
yeah. So
consider
in
the
this model, at the level of, I mean, potential that we derived, is very similar to the single field slow roll model.
yeah,
And
but you
so
have a vector field
basically,
which
epsilon, as you notice, epsilon and eta turned out to be small. So the level of
yes
non-Gaussianity
is
that would
slow
we
roll.
expect
Yeah.
is small, but it's slow roll suppressed, as you said. But as I mentioned, the amount of isocurvature perturbations that are produced from the other moduli, the one that, I mean, the embedding function, just two-point function, turned out to be not completely suppressed, but is of order of 100 of
Yeah,
the
I know, but
two-point
if we
function.
consider only two-point functions, so how we can speak about the inflationary effects? Because if we want to speak about the inflationary effects, we have to consider such non-Gaussianities. But my
No,
main
I mean in
question,
the slow models, usually, I mean, then the level of non-Gaussian turn out to be slow suppressed. So this is, I
okay,
mean, this is similar to
okay, I
those
understand.
models.
Yeah, I
I
understand. But
mean,
because you talk about the
from
observations,
non-Gaussianity aspect, I do not see any, I mean, interesting or nice probe within the setup. The the part which is maybe I mean, observable is the isocurvature field, and yeah, isocurvature
yeah,
contribution is
but
not
the
negligible.
sorry, my question is going to be I'm sorry, but I'm wondering because if you talk about the isocurvature, but you didn't consider the, uh, I know your idea and your opinion about the two-point functions, but when you talk about the isocurvature, usually people consider the bispectrum and higher orders to consider such effects if they want to talk about inflationary cosmology. But my main question is about the damping of vector fields of your magnetized holographic scenario.
Yeah.
Because there are many other beautiful visualization and also illusion, but how we can compare these theoretical results with observations, because our observations is based on some other models, uh, because your vector field will not receive to us by to detect by our satellite, Planck satellite.
So that magnetic field that I mentioned is just the higher dimensional magnetic field that provides the chiral symmetry breaking. So this is not on the D3 brane. So this is a magnetic field that breaks the chiral symmetry. And so it's basically different from the sort of vector field or magnetic field that you are just referring to. Maybe, I mean, that was the source of the confusion or the question that you asked. So the magnetic field was just one of the ingredients in the higher dimensional theory in order to just break the
Symmetry.
just break the symmetry. And
Yeah,
it's
I
not
understand.
related to the observable, I mean, to the cosmological magnetic field or the
So you
vector.
want to use such breaking symmetry to produce other materials like the uh,
Yeah,
Higgs?
as I mentioned, you from that magnetic field, you would obtain just you would see how your just dilaton, the profile of the dilaton in terms of rho and L should be in presence of that B. So let me, I
Thank you.
mean, maybe I have to go back to this equation. This equation.
Sorry.
So the presence of this B induces a running in the gauge coupling. I
Yeah,
mean,
thank
this
you.
one,
Thank you. I understand. Thank you so much.
no problem.
Thank you. Thank you.